Hello again, everyone. We're on 8.4 logarithmic and exponential equations. Um, Solving them. Use your log laws, okay? Laws of logs. Helpful identities here. This is the change of base identity. That's also helpful. All these are fair game. Anything that can help you to solve equations. Next one, useful properties. Okay, 1, 2, and 3. Let those help you as well to make your equations look different so you can get to a solution path. Here's a nice handy little flow chart if you want to think of it this way. A logarithmic equation contains one or more logarithmic terms with a variable in the argument. There's always a restriction on the variable. Okay. Step to solve it. State the restrictions. Apply your log laws to simplify. That's the whole goal here, is to make it look easier to solve. Is there a log term on both sides? If yes, then your path is faster. Write the equation as this. Compare the arguments only. Solve for x, and then reject any extraneous roots. Okay? Remember, the logarithm of a zero or negative number is undefined, so you have to look at the argument. Has to be greater than 0. Okay? To identify if a root is extraneous, substitute the root into the original equation and check whether all of the logarithms are defined. Okay, state your answer as an exact value. If there's not a log term both sides, go to no, then follow this chart where it says change to the exponential forms, then solve for x, and then do the rest of the same stuff. Let's get into some examples. Okay. Okay, I have log base 4 of 5 times, or log base 4 of 5x plus 1 equals log base 4 of x plus 17. Let's check for restrictions. Needs to be greater than 0, the argument, so x is greater than negative 17. The other restriction, 5x plus 1 must be greater than 0. X must be greater than negative 1/5. Okay, so those are our restrictions. I have a log base 4 term on both sides, so I can just make the two arguments equal. And then that's 4x equals 16, x equals 4. I'm not going to check everyone, but you can check x equals 4. First of all, 4 is greater than negative 1/5, greater than negative 17, so it has a defined solution, has a defined logarithm. Let's algebraically check it. So log base 4 of 5 times 4 plus 1 equals log base 4 of 4 plus 17. Log base 4 of 21 equals log base 4 of 21. Left side equals right side. That's a check. Letter B. Log base 2 of x minus 6 equals 3 minus log base 2 of x minus 4. Well, let's apply some log laws here. I have log base 2 of x minus 6 equals, I'm going to rewrite that 2, a little trick here. I'm going to rewrite that 3 as a log base 2 of 8 minus log base 2 of x minus 4. Why does that help us? Let's take a look. Let's apply some log laws. So log base 2 of x minus 6 equals the quotient rule, log base 2 of 8 divided by x minus 4. You know what I forgot to do? X minus 6 is greater than 0. Therefore, x must be greater than, x must be greater than 6. I forgot to do restrictions. X minus 4 is greater than 0. X is greater than 4. Okay. Let's see. I have the log base 2 on both sides, so I'm going to compare the arguments by making them equal to each other. And that will give me a quadratic. X minus 6 times x minus 4 equals 8. X squared minus 10x plus 24 equals 8. X squared minus 10x plus 16 equals 0. And then factor that, x minus 8 times x minus 2 equals 0. My solutions are x equals 8, x equals 2. I'm a little bit out of room here. I'm going to trust that you can check this, do the check step by yourself, but I'm going to reject some things here. So x must be greater than 4, x must be greater than 6. Well, that's done. This is your solution. Okay, log base 3 of x squared minus 8x to the 5th equals 10. So let's apply some log laws here. That is power law, log base 3, 5 times log base 3 of x squared minus 8x equals 10. Divide both sides by 5, log base 3 of x squared minus 8x equals 2. Restrictions, sorry. Greater than 0, x times x minus 8 is greater than 0. So x must be greater than 0, and x must be greater than 8. Okay, in this case, x has to be greater than 8. Well, actually, nope, x has to be greater than, yeah, so if it's greater than 0, let's say it's 1, it's going to be a negative number, right? So this one's out. X is greater than 8. That's your only restriction. Okay, so let's continue. I have, let's turn this into exponential form. 3 squared equals x squared minus 8x. That's 9 equals x squared minus 8x. That's 0 equals x squared minus 8x minus 9. That's 0 equals x minus 9, x plus 1. That's x equals 9, x equals negative 1. I'm going to reject this because I have a restriction x is greater than 8, so that is your solution, x equals 9. Next one, log base 2 of x plus log base 4 of x equals 6. Okay, I have a problem here. I can't apply the log laws because I have a base 4 and a base 2. Okay, so I need to use the change of base identity. So log base 2 of x equals, log base 2 of x plus, let's apply the change of base identity. I can choose any base. Well, I'm going to choose the base 2. That's strategic because I want to match it with this 2. Okay, so log base 2 of x, this is the change of base identity, log base 2 of 4 equals 6. More log laws, folks. Actually, let's simplify. Okay, log base 2 of 4, that is just 2. So that's divided by 2 equals 6. Let me multiply both sides by 2. So I have 2 log base 2 of x plus log base 2 of x equals 12. Okay, I'm going to apply the power law in reverse here. So that's log base 2 of x squared plus log base 2 of x equals 12. Okay, don't be tempted. You see this plus sign? Don't be tempted to say that's 3 log base 2 of x. No. Okay, that's not a log law. Let's apply the product law here. So that's log base 2 of x squared times x. And then that equals 12. Okay, I get log base 2 of x cubed equals 12. Okay, let's put it in exponential form. 2 to the 12th equals x cubed. If I take the cube root of x to the 12th, that equals cube root of x cubed. That's 2 to the 4th equals x. And that's 16 equals x. You know what I forgot to do, folks? I forgot to do the restrictions. So the restrictions here, I have an x, and an x, so x must be greater than 0. And 16 is definitely greater than 0, so that is a solution. Okay. Next one, this really scary looking one. Oh my god, look at that. Okay. Yeah, here's a hint. Unwind all the algorithms. Or sorry, unwind all the logarithms. Okay, what does that mean? So here's my base. This is what the exponent becomes, right? Base, exponent, this whole thing in the middle here, that's the argument. Okay, so start unwinding it like this. 1/2 equals 1/2 to the 1 exponent equals log base 4 of log base 2x. Okay, unwind it some more. Here's the base. Now this is the exponent. Here's the argument. So what happens there? Let's unwind it some more. So 4 to the 1/2 equals the argument log base 2 of x. Okay, 4 to the 1/2 is 2, and that's log base 2 of x. One more time, 2 raised to exponent 2 equals, 2 raised to exponent 2 equals x, 4 equals x. And you know what? I forgot to do the restrictions again here. X must be greater than 0, and 4 is definitely greater than 0. Okay, so the solution has a defined log. Next page. Okay, solving exponential equations using logarithms. Okay, recall that an exponential equation contains a power with a variable as an exponent. So steps. Can you write both sides of the equation with same base? If yes, then it makes it a lot easier. Change the same base, compare exponents, solve for x. State your answer as exact value. If no, then you have to convert to logarithmic form or take the common log of each side. Once you convert to log form, apply the power law if an exponent remains, solve for x. If you take the common log of each side, apply the law of logarithms, and continue the path to solve for x. State it as exact value unless we say otherwise, okay? Okay. Quick review here. Write 32 with a base of 2, so we know that's 2 to the 5th. Okay. Write cube root of 16 with a base of 2, so that's cube root of 2 to the 4th. Well, that is 2 to the 4/3. Simplify by converting each term to a common base, so more review. So this is, I have a 64/8. Let's put this all in terms of, I think base 2 might work, right? Base 4 doesn't work. Base 2. So 64, that's 2 to the 6th, okay? 2 to the 6th, so that's 2 to the 6th to the 3x plus 1 divided by 2 to the 3rd times 5x minus 3 times 2 to the 4th to the 2x plus 5, okay? Let's use the power law for exponents. 2 to the 18x plus 6 divided by 2 to the 15x minus 9 times 2 to the 8x plus 20. Let's combine them all. So that's 2 divided by these two. So let's do the quotient law. So that's 2 to the 18x minus 15x is 3x. Okay, and then 6 minus negative 9 is 6 plus 9, that's 15, and then that's times 2 to the 8x plus 20, and then that equals 2 to the, we're adding exponents, okay, so that's 11x plus 35, okay. Good practice for example 2, solve algebraically. So this one we can make a common base, okay, so first I'm going to start with 5 to the 3x, and 5 to the 4x minus 2, that equals 5 to the negative 1 to the negative x minus 4. Left side I'll simplify, that is 5 to the 3x minus 4x plus 2 equals 5 to the x plus 4. I have the same base. I can make the exponents equal to each other, so that's negative x plus 2 equals x plus 4. That's negative 2 equals 2x, negative 1 equals x. I can do a quick check here. That's 125 to the negative 1 divided by 5 to the 4 times negative 1 minus 2 equals 1 over 5 to the negative 1 minus 4. And that is, evaluate all that, that's 125 equals 125. Check. Okay, next one, 2x equals 2 to the x equals 2,500. Take the log of both sides. So this one we must take the log of both sides. I'm going to take the common log of both sides. Log to the 2x, 2 log of 2 to the x equals log of 2,500. Apply some log laws here. Okay, we free up that x. I'm going to divide both sides by log of 2. Okay, and then if we leave it as an exact value, here it is, exact, okay, because these will not evaluate to a whole number. Or if I ask you to give me decimal form, let's do it to the nearest hundredth, so it's 11.29. Okay, so exact versus rounded. Okay, or the other way, if we want to, if they ask, write it as a single logarithm. Okay, remember I have a base 10 here, right? Base 10, right? So what I can do is use the change of base identity in reverse. So I have x equals log base, I'll put that in here so you can see it happening, over log base 10 of 2 as a single log. That's x equals log, now the base is 2, and then the argument is 2,500. Okay, and then you can check that on your calculator. It works. All right. Next page. 5 to the x minus 3 equals 1,700. So this one, we'll have to take the common log of both sides. Okay, power law. Oops, make sure you use brackets here so we know that that is that. X minus 3 equals log of 1,700 divided by log of 5. And I'm going to add 3 to both sides, so that's 3 plus log of 1,700 over log of 5. Okay, you can calculate the decimal here. The other thing, if they ask you for a particular form, you can take this because this is both base 10. You can use your change of base identity to rewrite it. Let's go ahead and rewrite it just for fun. That's x equals 3 plus log base 5. Okay, so 3 plus log base 5. Take a look at where you get that new base from. So log base 5 of the new argument, which is 1,700. Okay, so if I do the calculation, let's make an estimate here. That is 7.62, rounded 7.62. Okay, and then that's calculating this. Let's calculate this without the change of base identity. 3 plus log of 1,700 divided by log of 5. Same answer, so 7.62. Be able to convert back and forth, okay? Okay, 6 to the 3x plus 1 equals 8 to the x plus 3. Again, log laws, right? Let's apply our log laws here. Or sorry, common log of both sides, 6 to the 3x plus 1. That'll allow us to free up that exponent that's stuck up there, right? That's 3x plus 1. Make sure you use brackets. That's log of 6. Then that's x plus 3. That's log of 8. Okay, this one, let's distribute log of 6. So that's 3x log of 6 plus log of 6 equals, let's distribute it on the other side, x log of 8 plus 3 log of 8. Let's group all the x's together. So I'm going to group them on the left side. So 3x log of 6 minus x log of 8 equals 3 log of 8 minus log of 6. So I'm rearranging the terms of the x's on the left side and then the non-variable terms on the other. I'm going to take out or factor out an x. So that's 3 log of 6 minus log of 8 equals 3 log of 8 minus log of 6. Divide both sides by 3 log of 6 minus the log of 8. I get 3 log of 8 minus log of 6 divided by 3 log of 6 minus log of 8. Let's keep simplifying this. I'm going to bring this up here. I can apply some quotient law here. So, but before I do that, I'm going to go log of 8 cubed minus log of 6 divided by log of 6 cubed minus log of 8. Okay, quotient law on the top. Okay, so quotient law, remember, I'm subtracting two logarithms. I'm going to divide them, right? Divide the argument. So I do this. So that's log of 8 cubed divided by 6 divided by log of 6 cubed divided by 8. Okay, let's continue. 8 cubed is 512 divided by 6. Well, I'm going to get a decimal, so I'm going to leave it as log of 512 divided by 6 divided by log of 6 cubed. 216 divided by 8. That's actually 27. So 6, let me try it again. 6 cubed divided by 8. That's 27. So it's 27 on the bottom denominator. Okay, and then let us do this. I'm going to further, let's combine this using our change of base identity. So that's log base 27. Okay, of the argument, log base 27. Okay, of the argument 512 over 6. Okay, and then we can leave it like that. Okay, and then if you're evaluating this, so as a value, that's log base 27 of 512 divided by 6. Okay, I get 1 point, if I'm estimating, 1.35, right, rounded to the 100th. Okay, so try, when you state it as an exact value, try to reduce it down to its lowest possible form, like logarithm, simplest form, where it's stated as 1 log. Okay, that's good practice with your laws of logarithms. All right, next one. 2 times 3 to the x minus 2 equals 7 to the x. So this one, I'm going to take the log of both sides again. So that's log of 2 times 3 to the x minus 2 equals log of 7x. Okay, this one, I will do log of 2 plus, so the product law, log of 3 to the x minus 2 equals log of 7 to the x, power law, okay, next log of 2 plus, I'm going to distribute that log of 3 across, so that's x log of 3 minus 2 log of 3 equals log of 7x. Tons going on here. I'm going to collect the x's on one side. So I'm going to go x log of 3 minus, one thing I forgot to do here. This one, let me rewrite it so I can save a step here. So equals, let's use the power law here. So that's x log of 7. Okay. Now collect the x's on both sides. X log of 3 minus x log of 7. So x terms on the left side, all the other terms on the other. So 2 log of 3 minus log of 2. Okay. Factor out an x. X log of 3 minus log of 7 equals 2 log of 3 minus log of 2. Okay, divide both sides by log of 3 minus log of 7. That is 2 log of 3 minus log of 2 divided by log of 3 minus log of 7. Let's combine things using some more log laws. So that's log of 3 squared minus log of 2 divided by log of 3 minus log of 7. Okay, I'm going to use my quotient law. So that is log of 3 squared. Let's call that 9. So log of 9 divided by, oops, oh, wow, hang on. Log of 9 divided by 2. Okay, so remember, quotient law. Log base c of m minus log base c of n equals log base c of the argument m divided by n. Okay, so that's 9 divided by 2. And then log of 3 divided by 7. Okay, I have base 10 on both top and bottom. So what I'm going to do is I'm going to use a change of base identity. So log of base 3 sevenths of the argument 9 halves. Okay, if you do this on a calculator, estimated value, so 3 divided by 7, and then 9 divided by 2, I get roughly equal to negative 1.78. Okay. Okay, couple more to go, folks. Oops. Let's see what happened here. Oh, someone actually did this work. I'm going to erase it, and then I'll do the work for you. Okay, just a second. All right, number 5. The following shows how Giovanni attempted to solve the equation 2 times 3c to x equals 8. Identify, describe, and correct his errors. Well, this is a good textbook problem. Right here, folks. 2 times 3 to the x, whoa, does not equal 8. You cannot just multiply that 2 and the 3, right? Because it has brackets and there's an exponent there. That's the error right here. No. Okay. Let's do this. I'm going to divide both sides by 2. I have 3 to the x equals 4. Convert to logs. So that is log base 3 of 4 equals x. Okay, and then rounded to the nearest hundredth, 1.26 equals x. Okay. Next one, number 6. State the decimal approximation to the nearest hundredth. I'm also going to give exact values too. Exact. Let's be exact. All right, let's do this. I'm going to take the log of both sides, so common log. 2 times 5 to the 4x plus 1 equals log of 6 to the x plus 2. Okay, let's apply the product law. Log of 2 plus log of 5 to the 4x plus 1 equals log of 6 to the x plus 2. Let's apply some product law here. So plus 4x plus 1 log of 5 equals product log, power law again, log of 6. Okay, I have log of 2 plus 4x log of 5 plus log of 5 equals, I'm distributing the log term, so x log of 6 plus 2 log of 6. Let's collect all the x terms on one side. 4x log of 5 minus x log of 6 equals 2 log of 6 minus log of 5 minus log of 2. Okay, factor out an x. That is 4 log of 5 minus log of 6 equals 2 log of 6 minus log of 5 minus log of 2. Okay, divide both sides. I get 2 log of 6 minus log of 5 minus log of 2 divided by 4 log of 5 minus log of 6. Wow. Okay. Continuing. X equals log of 6 squared minus log of 5 minus log of 2 divided by log of 5 to the 4th minus log of 6. Why are we doing all this? Because it says put it into a form where it's one single log like this. So let's work at this, folks. We'll get there. X equals log of 6 squared divided by 5 minus log of 2 divided by log of 5 to the 4th divided by 6. Okay, x equals log of, let's do more quotient law, log of 36 fifths divided by 2. Okay, and then log of 625 sixths. X equals log of 36 tenths divided by log of 625 sixths. Okay, let's bring it over here. Need more room. That's log of, let's reduce, 18 fifths divided by log of 625 sixths. Okay, and then I can't reduce anything anymore. What we can do here is let's use the change of base identity. I'm just thinking aloud here. Yep, change of base identity. Okay, that's x equals. Okay, the argument in the denominator becomes the new base, log of 625 sixths of 18 fifths. Okay, that's your exact value where A, B, C, D. So A equals 625, B equals 6, C equals 18, D equals 5. Estimated value, x equals nearest hundredth, 0.28. This is a challenging one, lots of steps.